Alright, in this video we're going to talk about rationalizing denominators. So what that means is, when I have a rational expression, right, an expression that's a fraction, if my denominator is not a rational number, in other words, if my denominator involves a square root in some way, well, that's not a rational number. And for some reason, mathematicians don't like to have roots or radicals in their denominators. I don't know why that is, but that's just one of those rules that mathematicians came up with. If you're solving a problem and you end up with a square root or a radical of some kind in your denominator, we need to get rid of it so that our denominator is just a rational number, just basically a whole number in most cases. Right, so the way we do that, when we have a square root in the denominator, if we have something like 1 over the square root of a, well, this is something we saw when we talked about fractions. We can multiply that fraction times 1. Right? You can multiply anything times 1, and it doesn't change the value of what you're working with. Right? But we're going to choose that 1 in such a way that is advantageous to us. Right, so this time, when I have 1 over the square root of a, I'm going to multiply that times the square root of a over the square root of a. Right? Root a over root a just equals 1. Right, so I'm allowed to do that because I'm really just multiplying this by 1, which doesn't change the value of what I'm working with. Right, so when I multiply it by root a over the square root of a, well, now that I'm multiplying fractions, I just multiply straight across. Right, so 1 times the square root of a equals the square root of a. And the square root of a times the square root of a equals a. Right? And just to show you how that works, the square root of a times the square root of a is the square root of a squared. And remember, the second power cancels out the square root, and we just have a. Right? So when I multiply by the square root of something times the square root of that same thing, the square roots basically cancel each other out, and I just get that number underneath, which is the a. Right? This is why that is. Root a times root a equals the root of a squared, and the root cancels out the second power. Alright, so if we have just a square root in our denominator, we rationalize it by multiplying both the numerator and denominator by that same square root. Right, and we'll do an example of this in a couple minutes after I talk about this other way to rationalize. We'll do an example of each of these types. Right, so that's if we just have a single square root in our denominator. If we have an expression in our denominator that involves a square root, but it also involves another number, like being added or subtracted, it gets a little more complicated. It's the same basic principle, but I have to multiply by something a little bit different. Right, so if I have 1 over the square root of a plus b, right, notice here that the a is underneath the square root, but the b is not. Right, again, pay attention to the details. If that square root bar goes all the way across that b as well, it's a completely different problem. Right, so pay attention to those little things. Right, so it's 1 over the square root of a plus b. I'm going to multiply it by 1, but I'm going to write that 1 in such a way that when I multiply it, it gives me what I want, which is not a radical in the denominator. Right, so I'm going to multiply by the square root of a minus b over the square root of a minus b. Right? That expression right there, root a minus b over root a minus b, that equals 1 because it's the same thing over itself. Right? And that expression there, that square root of a minus b, we call that the conjugate of this other expression. Right? So the square root of a plus b and the square root of a minus b, those are what we call conjugates. Right? They're similar expressions, but we just change the sign in the middle. One's a plus and one's a minus. And the reason we do that is because when we multiply conjugates together, right, the square root of a plus b times the square root of a minus b, what happens is that the square roots actually end up canceling out. So just to kind of show you how that happens, if I use the FOIL method, which again is something we haven't talked about yet, but hopefully you've heard of that before. If I do the square root of a times the square root of a, just like we saw up here, that's going to equal just a. Right? That's the square root of a squared, which equals a. Alright, so I get a. When I do the square root of a times minus b, it's minus square root of a times b. When I do the positive b times the square root of a, it's going to be plus the square root of a times b. And when I do plus b times minus b, that's going to be minus b squared. Right? So you're going to say, well, we didn't really cancel out the square roots because these two terms here still have that square root of a. But they actually don't, because, well, they do, but look what happens with them, right? We have a minus square root of a times b and a plus square root of a times b. Those two cancel each other out because one's a minus and one's a plus. So we end up with a minus b squared, right? Which is what we have up here in our denominator of that original expression that we started with. Right? So if we want to rationalize an expression or rationalize a fraction that involves a square root expression like this, we multiply by the conjugate on the top and the bottom, right? We just change the sign from a plus to a minus. If this was a minus here, we would then multiply by it with a plus, right? Because when we multiply by the conjugate, it cancels out all those roots, right? And multiplying by a conjugate is another one of those little mathematical tricks that comes up not just when you're rationalizing denominators, but it comes up in a lot of other things as well as you move up through precalculus and calculus classes. Every once in a while, like you're stuck on a problem, you don't know how to proceed. If you multiply by the conjugate, you can go and you can finish off the problem. Right? So it's one of those things that does come up every once in a while. Right? And then notice when we do this, we have that square root in the numerator of the fraction, but our denominator is just a minus b squared. It no longer has a radical there, so we've rationalized the denominator. All right, so those are the two methods we have for rationalizing denominators. I'm going to pause this now and erase this stuff and then put up a couple examples where we actually do some problems where we do this. All right, a few examples here of rationalizing denominators. So the first one, we have 2 over the square root of 3, and we don't want that square root in the denominator. So since it's just a single square root there, to rationalize this, I just multiply by root 3 over root 3, right? Whatever that square root is, I just multiply it on the top and the bottom. Because remember, root 3 over root 3 equals 1. I'm allowed to multiply anything times 1 because it doesn't change the value of this 2 over the square root of 3, right? All it changes is its appearance. Right, so when I multiply these, 2 times the square root of 3 is 2 square root of 3. Right? Remember, when I'm multiplying a whole number times a root, that doesn't become the square root of 6. Right? I can only multiply those together if the number here is also, or if both of those numbers are inside square roots, I can multiply them together into a single square root. If I have one number in a root and one number that's not in a root, I cannot mix them. I just put the 2 on the outside and the square root of 3, or the 3 inside the square root, is just 2 times the square root of 3. Right, and then square root of 3 times the square root of 3 there, since both of these are square roots, I can multiply those together in a single square root and I get square root of 9, and then the square root of 9 just equals 3. Right, so I get 2 square root of 3 over 3. Right, that is equivalent to 2 over square root of 3, but now we don't have that root in the denominator, which, like I said a few minutes ago, mathematicians just don't like roots in their denominator, so when we get one, we have to do something like this to get that root out of the denominator. All right, and if you want to check it out, if you have a calculator handy, you can type in 2 divided by square root of 3 and then 2 times root 3 divided by 3 and see that they actually come out to the same value. Right, those two things are equivalent; they just look a little bit different. Right, and this type of stuff comes up, like rationalizing denominators. It comes up especially when you start dealing with trigonometry. A lot of the numbers that come up in trigonometry involve square roots. And so a lot of the answers you get involve square roots and denominators, and then you have to rationalize. So it does come up as you move forward in mathematics, right? The next one here, 1 over the 3rd root of 5. This one is going to be a little bit more, not really more difficult, but a little bit tricky to figure out what to multiply by, right? I don't have a square root here. I have a 3rd root. All right, so I'm still going to multiply by something to cancel out this 3rd root. But if I just multiply by the 3rd root of 5 over the 3rd root of 5, well, is that going to cancel out the 3rd roots? Let's think about it. If I do the 3rd root of 5 times the 3rd root of 5, that's going to give me the 3rd root of 25. And what's the 3rd root of 25? I don't know. There's some number that if I multiply it by itself 3 times, it equals 25, but it's not going to be a nice whole number that I'm going to be able to calculate. Right? So in order for this to work, I need this to be, like up here, the 3 times 3 was 9, and I can do the square root of 9, right? Because 9 is 3 squared. Well, in order to be able to simplify this cube root here, I need the cube root of 5 raised to the 3rd power, right? The power that I have here, and let me just kind of write this up here, right? That was the 3rd root, or sorry, that was the square root of 3 squared, and the square root canceled out the 2nd power. The same thing has to happen here. Right, the cube root of 25 is the cube root of 5 squared. The 3rd root does not cancel out the 2nd power, right? Because they're not the same. So in order to make this work, I need to have the cube root of 5 to the 3rd power, and then the cube root and the 3rd root and the 3rd power will cancel out, and that will just equal 5. Right? So in order to cancel out a root, I need to make sure that the exponent that's inside there matches the root that I'm taking, right? If I have a square root, I just need this to be 3 squared, and then they're going to cancel out. But if this is the 3rd root, I need it to be 5 to the 3rd power in order for those 3's to cancel, right? Which means I can't just multiply this by the cube root of 5. I have to multiply this by the cube root of 5 squared, right? Because I need that 5 when I multiply these together. I need to get a 5 raised to the 3rd power in order for it to cancel, right? I hope that makes sense. With square roots, it's pretty easy because if I just multiply by a square root times a square root, whatever's underneath gets squared and they cancel out, and it's just pretty straightforward. But if it's a higher root that I'm taking, a third root or a fourth or a fifth root, I usually have to multiply by something raised to a power here to get the exponent to match the root. All right, so anyway, when I do that, up in the numerator, I'm going to get the cube root of 25, right? Because 5 squared equals 25, so that just becomes the cube root of 25. In the denominator, when I multiply these two together, I'm going to get the cube root of 5 to the third power. Right, it's 5 to the first here times 5 to the second. The laws of exponents say add those exponents together, so I get 5 to the third. And then the third root cancels out the third power, and that's how I get just a 5 in my denominator. And I no longer have a radical now in the denominator, so I've rationalized the denominator. All right, so that one is a bit trickier than that first one that we saw up above, because we're not just taking a square root, we're taking a third root there. All right, the last one, 3 over the square root of 5 plus 1. Here, I don't just have a square root in my denominator. That square root is being added to another number. Right, so here, if I try to do square root of 5 over square root of 5, if I try to multiply those together, when I multiply this, I would have to distribute that square root of 5, which is going to cancel out this square root here. But when I multiply the square root of 5 times 1, that's going to equal the square root of 5, and I'm still going to have a square root in the denominator, so that's not going to do the trick of what I want to do, which is get rid of the square root that's in the denominator. Right? So remember, when you have that addition or subtraction here, that's when you need to multiply by the conjugate of that expression, the square root of 5 minus 1. Right? So don't just multiply by the exact same thing. If I multiply this by the square root of 5 plus 1, just to show you what happens in that case, if I multiply the square root of 5 plus 1 times the square root of 5 plus 1, the root 5 times the root 5, that will cancel out. That's just going to equal 5, right? Because that gives me the square root of 25, which is 5. But then when I do this, I get plus the square root of 5. When I do these, it gives me another plus the square root of 5, and then plus 1. And these plus square roots of 5 are not going to cancel out because they're both positive. And so I haven't gotten rid of the square root that's in my denominator. Right? In order to get rid of it, I need to multiply by the conjugate. If this one's a plus, I need to multiply by the same expression, but with a minus in the middle. Right, so when I do that, I get 3 times the square root of 5 minus 1 over the square root of 5 plus 1 times the square root of 5 minus 1. And now if I multiply all this stuff out, well, if I distribute that 3 in the numerator, that's going to be 3 square root of 5 minus 3. Right, remember, when I multiply the 3 times the square root of 5, that's not the square root of 15, that's 3 times the square root of 5. Right, I cannot mix those numbers because one's in the square root and the other one isn't. Right, 3 times minus 1, that's minus 3. All right, and then when I do multiply these conjugates down here, root 5 times root 5 just equals 5. Right, again, that's the square root of 25, which we can simplify to 5. 5 times square root of 5 times negative 1 is negative square root of 5. Positive 1 times square root of 5 is going to be plus square root of 5. And then 1 times negative 1 is going to be minus 1. Right? And the negative square root of 5 cancels out the positive square root of 5. So I get 3 root 5 minus 3 over 5 minus 1, which is 4. And now I've got a rational number in my denominator, so I've rationalized my denominator. All right, so that's what happens when you don't have just a square root or just a cube root. When you have addition or subtraction there, you have to multiply by that conjugate expression in order to actually eliminate the square root. All right, like I said a few minutes ago, multiplying by a conjugate is a pretty useful tool throughout mathematics. It comes up here and there, as you continue forward through algebra and precalculus and calculus. Every once in a while, you'll be sitting there listening to something your teacher's saying, oh, in order to solve this, we're going to have to multiply by the conjugate. It just kind of happens. It's one of those tools where, because one's a plus and one's a minus, if you keep the same numbers or the same expressions there but change that sign in the middle, when you multiply them together, the stuff in the middle always cancels out and allows you to like simplify things and move forward with your problem. All right, so that's the video on rationalizing denominators. Again, it's just one of those things mathematicians like their denominators to look pretty, and apparently pretty means not having a square root or a cube root in the denominator, and so it's just one of those things we have to do every once in a while.